Still talking about linear systems. We are looking at linear discrete systems and stability theory. In the last video, we considered linear continuous systems. So here, linear discrete systems and stability theory is our focus. I will look at topics like linear difference equations, eigenvalues and spectral radius, stable, unstable, and neutral directions, linear maps on the plane, linear torus maps, and stability theory. So the goal is to understand how eigenvalues determine long-term behavior of discrete dynamical systems. We saw something similar for continuous systems, but the approach will be a bit different for discrete systems. Just like, the idea of uh, equilibrium points in continuous systems and fixed points in discrete systems. The approach is somewhat different. So, introduction, a linear discrete dynamical system evolves by repeatedly applying a linear map, which is x sub n plus 1 equals a x n, x sub n, where x sub n is a d-dimensional, is in d-dimensional real number system, and then the matrix A is a D by D matrix, right? So the sequence Xn describes the system's evolution. Okay, so our goal is to understand when solutions converge, diverge, oscillate, or remain bounded. So, and then that takes us to uh, scalar linear differential difference equations. Scalar linear differential equations. Imagine we have xn plus 1 equals axn, where a is a real number. So the solution by iteration is xn equals a and x naught. How do we arrive at that, right? Xn plus 1 is axn, right? Xn plus 1 is axn. So we have xn plus 1 equals axn. What do? We know that at n equals 0, we have x 0 plus 1, that's x1 equals a x naught. Then at n equals 2, what happens? At n equals 1 rather, we started with 0. So at n equals 1, we have x2, that's 1 plus 1, and this is ax1. Now, x1 is already x naught, ax naught. So we have a into ax naught, and then that is a squared x naught. Okay, so you can see a pattern forming already. So at n equals 2, we have x3, 2 plus 1 is 3 equals ax2. Again, ax2 is a squared x naught. So we have a squared, I mean, uh, x2 is a squared x naught. And now this one becomes a raised to power 3 x naught. So if you continue like that all the way to n, so we see that xn plus 1 is equal to a n x naught. And that's how we arrived, because when you have 3, okay, this is x3, right? What's wrong here? X1 is a raised by 1. Okay, I think it's commensurate. So we see that xn actually, xn is an x naught, because x3 is a3 x naught, x2 is a2 x naught, x1 is a1 x naught. So that's what we have there. So xn is an x naught, as we see here. So this is what the whole thing behaves like. Okay, so, and then we see behavior here, that when the absolute value of a is less than 1, then you say that the system is stable. So everything depends on this a now. So the value of absolute value of a. So the absolute value of a, if it's less than 1, you have a stable system. If it's greater than 1, so the absolute value of if it's less than 1, it's stable. If it's greater than 1, it's unstable. If it's equal to 1, then you say it's neutral. Okay? It's neutral like that, because A is driving that system like that. So imagine this example that xn plus 1 is 0.6 xn. So, and if you take x naught to be 1, right? If you take x naught to be 1, xn is simply just going to be 0.6 raised to power n. Because if you take x naught to be 1, that's going to be, what do we have again? If you take x naught to be 1, so if this is 1, you just have a raised to power n. So, and that's what you're just going to have 0.6 raised to power n. So, as n goes to 0, I mean, xn goes to zero as n goes to infinity, because as n is increasing, this is a fraction, right? So, I mean, see what we are saying. As n increases, that expression goes to zero. So you have 0.6. Let's start with raised to power 1. Okay, that's 0.6. What if it's raised to power 10? Okay, I'll just take it in 10 so you can see how fast it's going towards zero. So if it's going to 10, so you see that's 0.006 something. Let me do 100, and then you see how it would have gone very so close to zero. So as n approaches infinity, this expression is approaching zero. That's what that simply means. Okay. So that's what we are going to demonstrate here with this Python code. Okay, I still have all these things here. I want to show them one after the other. I just clear outputs and then come back and do that. Okay, so here now we run this code just to demonstrate that this expression ends up going to zero at the end of the day. So it keeps declining and declining towards zero, because as n is increasing, this is moving towards zero like that. Then we have matrix difference equations. So if you consider xn plus 1 equals ax sub n, where a is a d by d real matrix. So the solution by iteration, like we saw already, is xn equals a power n x now. This is matrix now. So the behavior depends on the powers of a. So this power of a determines what happens to this system at the end of the day. So to understand a sub a power n, we have to study the eigenvalues. So in this case now, eigenvalues and eigenvectors. So we usually have the eigenpair consisting of the eigenvalue and the eigenvector, and that satisfies AV equals lambda V, which we talked a lot about under linear algebra. So AV equals lambda V, where lambda is an eigenvalue and V is an eigenvector. And the interpretation of this is that, okay, yeah, geometrically, the map A stretches V by factor lambda. That means if a matrix operates on a vector, so you see that the vector is stretched or compressed by the value of lambda here. Okay, so matrix operating on a vector actually it gets to shrink or expand the vector, right? And then we have the idea of spectral radius. So let lambda 1 up to lambda d be eigenvalues of A, different eigenvalues, by the way. So the spectral radius is actually given as rho of A, and that is the maximum of all the eigenvalues. So the maximum of all the absolute values of all the eigenvalues gives the spectral radius. And I mean, that has application in different fields. And that in mathematical biology, for instance, which is my field, um, it is this spectral radius that gives us the basic reproduction number, which gives an indication of if a disease is going to die out or it is going to spread like that. So we have that mathematical theory becoming something biologically meaningful. Okay, then we have stability theorem for xn plus 1 equals ax sub n, right? The origin is asymptotically stable, all right, if the spectral radius is less than 1. Okay, just like when we said if the basic reproduction number is less than 1, it means that the disease is going to die out, right? Unstable if the rho of A is greater than 1. So if the spectral radius is greater than 1, then the disease is going to spread. In the case of mathematical biology, so rho of A, which is the basic reproduction number in mathematical epidemiology in particular, if it is greater than 1, that means the disease is going to spread. Then it is neutral if rho of A is equal to 1. Well, in this case now, the disease is not dying out and it is not spreading. So it's more like when something has become endemic. It's like when we talk about malaria in a place like Nigeria. So malaria is people have taken malaria as regular part of life. Like some people even expect it. So it's like it has become endemic somewhat. Okay. So yeah, we have that kind of idea here. So imagine this matrix 0.50, 0.12. Well, because this is a diagonal matrix, the eigenvalues are simply 0.5 and 1.2. But you can see for the spectral radius here, is actually the bigger eigenvalue, which is 1.2. So it is going to drive the system, right? And because this is greater than that, so it means that we have instability going to happen here. So if I run this now, so we see that the eigenvalues are 0.5 and 1.2 from here, and then the spectral radius is 1.2. That's the dominant eigenvalue. and that determines the fate of the system somewhat. Okay, and then we go for unstable, and neutral directions. So each eigenvalue, okay, each eigenvalue produces a direction. So for eigenpair lambda and v now, the absolute value of lambda less than 1 is unstable, greater than 1 is, less than 1 is stable, greater than 1 is unstable, equal to 1 is neutral, right? So if we decompose that, any vector can then be written as x naught equals c1 v1 plus all that up to c dvd. Then we have that xn is c1 lambda 1 n v1 up to cd lambda d n vd. So each direction evolves independently in that case. So as you can see here, so in this case now you have the eigenvalue 0.5 and 1.2. So this one is moving towards stability and this one is moving towards instability, but this one dominates the system. The 1.2 dominates the system. So imagine this situation now where we have stable and unstable directions. For this matrix now, 0.8 is going the stable direction, 1.3 is going the unstable direction, but 1.3 is the spectral radius because it's the bigger eigenvalue, you know. So let's see what that kind of graph gives us here. So you see this now. So you have this trying to go down. Okay. Yeah, you have this trying to go down, and then you have, let's see, where's that one now? We have 0.8 and 1.3. 0.8. Okay, this is X and Y. So we have this stable and unstable directions in this particular situation here. So then we talk about linear maps on the plane. So let T of x be equal to AX, where A is R 2 by 2. So we have A to be a 2 by 2 matrix. So this defines a map of the plane because we are talking about plane now. So you need two axes. So this defines a map of the plane. So the types of behavior here, if all the eigenvalues are less than 1, we have a contraction. So that means that things are shrinking. If it's a disease now, the disease is dying out. If all the eigenvalues are greater than 1, you have an expansion. If it's the disease is expanding, but in another context, it's like you have something blowing up, right? Something that cannot be contained. So less than 1, it can be contained. Greater than 1, it can be contained. If it is mixed, you have a saddle, like there's a kind of confusion. So one is going towards contraction, one is going towards expansion. But you then have some trouble with that. So then it can also be complex when it is spiral in that case. And then the absolute value of lambda is, if the absolute value of lambda is equal to 1, then you have some kind of rotation. Okay. So imagine theta is 0.4 and r is 0.95. You then have this matrix now. Cos theta minus sine theta, cos theta. So you want to see a kind of spiral sink here. Of course, in this kind of spiral sink, you're saying it's a sink, right? So it means this thing is it's spiral, but it's converging towards something, so it's a sink means it's going inside. So that means it's still converging all the same, right? So we have a spiral sink in that situation. Then we can have linear torus maps too. So the two-dimensional torus is t squared, which is the two-dimensional real number system over the two-dimensional real number system, and the points are taken modulo 1. So a torus map is then xn plus 1 equals axn modulo 1, where A has integer entries. These maps preserve area and may be chaotic, right? And that can give us like the Arnold cat map where you have A to be 2, 1, 1, 1, so that xn plus 1 is axn mod 1. So this map is chaotic, it is ergodic, and it is also mixing. Now, the idea of ergodicity is that if you imagine tossing coins now, if you toss 1,000 coins, if you toss a coin 1,000 times, most likely you're going to get something like half. If it's a fair coin, you're going to get half 500 heads and 500 tails, roughly, right? On the other hand, ergodicity means that if you toss one coin 1,000 times, you're going to get that like 50% of head and tail each for a fair coin. In the same way, if there are 1,000 coins and you toss them at once, you're also going to get the same thing. That's the idea of ergodicity. And then you also have the idea of mixing in that case of Arnold cat map. And that can be represented here with that 2, 1, 1, 1. And you can see this here. So we can see that x mod 1, y mod 1 thing, and then it gives us this picture of the Arnold cat map. So x mod 1 here, y mod 1 on this other side. Okay. Then we'll move on to we have a try to do a complete worked example. So if you let A be 1.1, 0.3, 0.07, thankfully this is a triangular matrix, so we can just read off the eigenvalues. So the eigenvalues are 1.1 here on the x-axis, 0.7 on the y-axis. Okay, but then the spectral radius is the bigger of the two. The spectral radius is 1.1. If you take absolute value, so the bigger of the two is 1.1. So rho 1, which is the spectral radius, is 1.1, which is greater than 1. So in this case, we say the system is unstable because the spectral radius tells us that much. And then the geometry of this is that in the x direction, where we have 1.1, the system is unstable. In the y direction, the system is stable. So that gives us a saddle. But overall, the system is not stable because the spectral radius is greater than 1. So we can demonstrate that in this using this Python code right here. So we have a saddle dynamics. I think we saw something like this before now. Okay, we have a saddle dynamics. We have moving towards stability and instability at the same time from two wings. So then, in summary, for xn plus 1 equals axn, the behavior is determined by eigenvalues. We say that the spectral radius, the spectral radius is simply the biggest eigenvalue. After you've taken after you've taken ignoring these signs. So rho A is less than 1 it means convergence. It means you can contain the situation. Rho A greater than 1 is divergence. Rho A equals 1 is neutral. And the key ideas we have here is that matrix powers control dynamics. Then eigenvalues determine growth. Each eigenvector is independent. And geometry follows spectra. Torus maps lead to chaos, you know. And of course, that leads us to practice problems where you can, you can do iterations and see how things go. So solve all problems carefully, show all steps and justify your conclusions. So find the explicit formula for xn. Okay, then determine whether the system is stable. Compute this for x naught equals to compute limits. Okay, maybe I should try this. X sub n plus 1 is 0.4 xn. Well, I mean, we can already know that it's going to be 0.4 raised to power n, so it's going to approach zero still. So I think I shouldn't worry. Then we have scalar instability. Xn plus 1 is this. Find xn in terms of x naught. Okay, let's try this out. Is it not going to be the same thing still? I think it's going to be minus 1.3 raised to power n ultimately, because this is just a here. So describe the behavior of solutions. Is the origin stable? Try all that out. 3 and 4, eigenvalues and stability. We have 0.6 and 0.9. Find the eigenvalues of A. They are simply 0.6 and 0.9 because we have a diagonal matrix. Compute the spectral radius. The spectral radius is 0.9. That's a bigger eigenvalue. Classify the stability of the region of the origin. Of course, the stability, the system is stable because the two eigenvalues are less than the absolute value is less than 1, right? So for saddle system, this is blowing up, this is converging, this is expanding, this is contracting, right? So the eigenvalue is 1.4, 0.5. Identify stable and unstable directions. The x is the unstable direction, y is the stable direction. Sketch the phase portraits. Of course, we can try that to see that. Then we have 5 and 6. Find the eigenvalues. Of course, that's 1 and 0.8. Determine whether it is diagonalizable. Okay, you can check that out for diagonalizability. For something to be diagonalizable, right, you want to be able to write the matrix A. So matrix A is diagonalizable if you can write it as D PDP inverse, where P is matrix matrix of eigenvectors, matrix of eigenvectors. Okay, that's what P is. On the other hand, D is matrix, okay, better still, let me say diagonal matrix, diagonal, diagonal matrix of eigenvalues. So you just want to make sure that any eigenvector, whatever eigenvector comes here must correspond with the eigenvalue here. So if you are putting the one eigenvector in column 1, make sure that the eigenvalue in column 1 for D also corresponds with that one to avoid confusion. Okay. So therefore, complex eigenvalues now you can try find eigenvalues. This you can't read out the eigenvalues directly here, so you have to really do the work. Okay, then you have 7 and 8 now. You have trajectory computation. So compute x1, x2, x3. So you can just keep iterating to compute like that. You just multiply this by x naught, whatever you get, multiply by 1, 1 again. So I think won't that remain the same for the most part? Identify stable and unstable components and describe all that. Then you have for spectral radius here. Okay, so you have to really compute the eigenvalues here because we can't read it off like we do because this is the matrix is not like the ones we used to read off straight. And then you have these two other ones. So you want to try this out and see how far you can understand this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, question, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of this channel by clicking on join. There are 3 levels of membership with different levels of benefits, right? So we can hang out together to discuss whatever interests you on my channel. I can consult for you on something uh, that you may be struggling with. I can share my PDF notes of the courses I've been teaching with you, and so on and so forth. So the possibilities are there. So just check and become a member if you can. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.